All right, we're going to take a look at parametric equations in section 6.3 here. Um, First thing I'd like to do is point out that we've done a look at parametric equations before during the first semester. You might remember eliminating the parameter. We're going to be doing that again in this section as well. When you have parametric equations, what they are two equations uh, that define x and y as functions of t. So if we look at an example one here, these are the two parametric equations that make up the graph that we see to the right there. Now, there's three different graphs, and that's because we've restricted t on these three different intervals here. But if we didn't restrict t, if we just said, let t be any real number, then what this graph would look like is this entire graph going forever. But if we were to restrict the values of t, it would restrict the function or in this case, the relation, because it's not a function, in these three ways that we see here in A, B, and C. You can play around with this if you want. You can turn the mode on your calculator into parametric mode, and that's, remember, when you go to mode, oops, and if you change it to parametric, when you go to y equals, instead of saying y equals, it actually have an x and a y equals that you can define with t. When you hit this variable button, it'll put a t in. We're not going to spend much time graphing these like we did in the first semester. We looked at that a little bit closer. Just a reminder as to what defining these parametric equations, what it looks like when you graph them. These two equations defined for x and y again give us this horizontal parabola that we have shown on the right there. So let's get some practice again eliminating the parameter. These directions say to eliminate the parameter, which means we want to write these as one function, y in terms of x, and then identify the graph of the curve. What that means is we want to tell what it is. Is it a line? Is it a parabola? Is it a cubic function? So let's start with our eliminating the parameter using substitution. In order to do that, what we need to do is solve one of the equations for t and then substitute it in the other one. Well, because in the end we want y equals, I'm going to take this equation here for x. In fact, I'm just going to write it over here again. X equals 1 minus 2t. I'm going to solve that for t, and I'm going to put it into the other function so that in the end, I'm going to have y equals. So if I say that x equals 1 minus 2t, that would mean that 2t, I'm going to add the 2t over, and then I'm going to subtract the x over, would be 1 minus x, or t would be 1 half minus 1 half x. And now I'm going to put that in for t in the other function. So the other function is y equals 2 minus t, but for t, I'm going to put in this guy right here. Okay, and if I'm going too fast, if you don't see how I got something, please pause video, take a second to solve this for t. I'm sure you'll come up with that same thing right there. I don't think I made any mistakes. Let's see here. So I'm going to substitute that 1 half minus 1 half x here. And now we're going to solve this for y and simplify. We're going to first distribute that negative in there and get y equals 2 minus 1 half plus 1 half x. I need a common denominator here so I can combine some things together. That's 4 over 2. So we have 3 halves plus 1 half x here. Y equals, I'm going to just flip it around, put the 1 half x in front, plus 3 halves. That's it. That's a y equals x equation. It's clearly a line. It asks us to identify the curve. So I'm going to say, okay, it's a line. We could even be more specific and say it's a line that has a slope of 1 half, a y-intercept of 3 halves, but this should be good here. Okay, I think I actually have a spot down here where we could graph this. I'm just going to do a real quick sketch of what this would look like. So here's 1, 2. So we've got a y-intercept of 1.5 and then a slope of 1 half. I'm just going to sketch that in there. It should look good enough. All right, so what I'd like to point out here is that this says let t be any value. That means that this line goes on forever and ever. If it would have restricted t to certain values, then I would have put those values in to these two functions to find out what values of x and y I should have as my endpoint. So if we would have restricted t, it would have just given us a line segment instead of a line. But this one is a line. We'll talk about more about the segments later. Okay, so this one is, again, eliminating the parameters, so we'll do a little substitution. So I'm going to, actually this time I'm going to take this guy. This one looks pretty easy to solve for t, and I'm just going to say that t equals 1/3 y, or y over 3. I'm going to put that into our other function here. And you're probably saying, well, why would you do that way? You did it the other way in the last one, so that you had it as y equals. Well, this one here, we'll see in a second, is actually okay. Oops. So I have x equals t squared minus 2. This one is actually okay, because how this simplifies in a second, to leave in this form. So we're going to square that y over 3, and we have this right here. And in fact, I'm going to pull that 1/9 out as that there. And what I'm going to do is I'm going to get y squared by itself. So I'm going to add that 2 over and have that 1/9 y squared equals x plus 2. So I added 2 over to the other side. And then I'm going to multiply both sides by 9 and have y squared equals 9 times x plus 2. And this is what I meant about, this is a pretty legitimate way to leave this. And here's why. Maybe you remember, hopefully remember a little bit from last year about our conic sections. We had horizontal parabolas as well as vertical parabolas. This is the form of a horizontal parabola. Vertex is h comma k, and then 4p would tell us all sorts of good things about the distance between the focus and the directrix, or the vertex. So this is actually in the form of a horizontal parabola whose vertex is -2 because of the +2 right there, comma 0 because there's no k value. So I'm going to write that here. This is a horizontal parabola. And we know that the vertex is -2 comma 0. But what I'm also going to do is I'm going to solve this for y here by taking the square root of both sides. So this is totally okay because that is in the form of a horizontal parabola. Or we could take the square root of both sides. And remember, if you take the square root, you have positive or negative. And then the square root of the right side would be, well, the square root of 9 is 3. And then the square root of x plus 2, I'm just going to leave as the square root of x plus 2. So this is another legitimate way to leave that equation. Okay, this one I think is something that we've already graphed this year already. This is easier for us to graph right now. We are going to do horizontal parabolas like these in a little bit, just before spring break. So hopefully you'll remember then how to do that. But we've done the square root graphs this year already, where we know that y equals the square root of x. We have some pretty easy values to put in there. Any square roots. And we get the any perfect squares, I should say, and then we get their square roots as the y values. So we know that if we have y equals 3 square roots of x, we would just multiply all those y values by 3. So we'd have 0, 0, 1, 3, 4, 6, and 9, 9. And so these would be points from the vertex. Well, what's the vertex? This vertex of this square root function. Okay, remember square root functions look like this, right? But this one has a vertex of -2 comma 0. Hey, that sounds familiar. So we have, and actually we don't call it a vertex with square roots, I'm sorry. Square roots, it's just that starting point that's normally 0, 0. We're going to go back to -2, 0 and put that point right there. And then we're going to graph these points from there. So 0, 0, that's that point that we've already graphed, and then 1, 3 from that point would be right there. Oops, sorry. Right there. And then I can reflect that because of the positive negative. So we'd have another point right there. So this graph looks something like this. I think just having that one point is totally good enough here. So this is the square root function, but because of that positive negative, we also have this graph down here resulting in that horizontal parabola. So in case you hadn't picked up on this yet, this is the exact same function as what was graphed up here. These are the same two parametric equations. I keep calling it a function. You guys know it's not a function, it's a relation. It doesn't pass the vertical line test. Same relation as up above. Without restricting it, there's no restrictions on t here. This thing would go on forever and ever like this. And then if we restrict the values of t, then we only get segments of that horizontal parabola. All right, so now we're going to do another eliminating the parameter. This time, this is quite different. Substitution is not going to work in this one. You'll notice we have a cosine function, we have a sine function. So I'm going to show you a little trick here. What we're going to do is we're going to square, zoom in here a little bit, we're going to square both of these equations. And as we do this, you're probably going to be wondering, why are we doing this way? Just wait for it. There's a nice little step in a few minutes here that'll help make this make a little bit more sense. So what I've done is I've squared both of these equations, both sides, left and right, okay? And so that would result in the 2 being squared and then the trig function being squared as well. And then what we're going to do is, instead of substitution, what we're going to do is we're going to use that elimination, also known as linear combination, where we actually add the equations together. Normally when we do that to cancel something out. Nothing's going to cancel out here. But watch what happens when we add these two equations together. What I'm going to get on the left side is that x squared plus the y squared. So I'm going to add the two left sides together. And then I'm going to add the two right sides together. That would give us the 4 cosine of t squared plus the 4 sine of t, sine quantity squared. All right, and then what I'd like you to do is notice that we have a GCF right here. We're going to pull that 4 that we see common in both of those. We're going to pull that 4 out. And when we do that, I think you're going to see the whole reason why we did this. When we pull that 4 out, we're left with cosine squared plus sine squared, which hopefully we recognize as being 1. So we have x squared plus y squared equals 4 times 1, or x squared plus y squared equals simply 4. Okay, and if you need to write a little note to yourself, that this equals 1, that was a nice little trick that we had happen there. So look at that equation. Hopefully you recognize that. That is the equation of a circle. This is a circle with a radius of 2, because that's the radius squared, and the center at 0, 0, because there's no h and k value. So we just found the relation that this set of parametric equations equals. It's a circle with a radius of 2. So if you want to come up here and just draw a simple circle, I would do better than that. Actually, these are not very good tools here, but I'm going to try using one anyways, because why not? And it doesn't get centered on the origin. Why would it get centered on the origin? All right, so there we go. So I'm just going to say there it is. It's a circle with a radius of 2. There we go. That's what that equation ends up being. Or that's what those two parametric equations end up representing. And this doesn't restrict t between any values except 0 to 2 pi. But think about it. Between 0 and 2 pi, we get every point that we need on that circle. Basically, we have a unit circle there with a radius of 2. So it's a unit circle that's been scaled by 2. All right. Now we're going to go in the other direction here. In the last couple of examples, we eliminated the parameter in order to come up with a function or a relation with y and x. Now we're going to give you 2 points right here, a and b, and instead of writing the equation of a line as a function, we're going to write the 2 parametric equations that would represent that line. So if you can ignore that solution, I should just get rid of that. It just makes things a little bit more confusing, I think, than it has to be. But what I'd like you to do is notice this drawing that we have here. I have these 3 points that I put on this drawing. Okay, you already have these. Let me get back to where you are right there. So you have the blue and the red vectors drawn in there. We're going to use vectors to help us get our 2 parametric equations. All right, so we're going to put this point here, we're going to call O, the origin. This point we're going to call A, that's the point A that they give us, that's a negative 2, 3. And then the other point that they give us is B, that's actually this point right here, 3 comma 6. So we've already got a lot of stuff going on this graph. Really what you have right now is the graph of this point and this point, okay? And what we're going to do is we're going to draw a vector from this, from the, in standard position, a vector to that point, and then we're going to add a scaled vector that goes through our other point and say that the sum of those two vectors will equal that vector right there. Okay, so the vectors that we have are OA, which is that blue one, and then the resultant vector that we're going to end up with in the end is actually this OP here, and P is just an arbitrary point that we're going to make up called XY. That's this point that we're putting right there in this little drawing that I drew up here. Okay, so what we want to start with is the fact that, okay, we know vector OA is that negative 2, 3. Okay, that's that blue one that we have. AB, which is this one right here, we don't have in component form. So we want to get that green one I just drew in component form. So we need to take our head minus tail rule and take 3 minus negative 2, which is 5, and 6 minus 3, which is 3, and that is the component form of that vector AB. Okay, and all that means is, you know, if I started from that point where the blue vector ends, if I went to the right 5 and up 3, that would get me to that new point B that's right there. Okay, all right, so what does that green one have to do with getting to that point P? Well, now what we're going to do is we're going to actually take that vector, that green one, we're going to scale it out so that it hits that point right there. Okay, and our scalar is going to be T. So here's what we want to do. Let's start with this here. We know that that vector OP in component form is XY. I'll try to keep my colors the same. So when we say that vector OP, we're talking about that red one that we have drawn here. So in component form, that's XY. That would equal vector OA, that's the blue one that we have, OA, which is negative 2, 3, plus that vector AP. Well, AP, we don't know what that is, but we do know that it's AB, which is right there. I covered it up, that purple one covered up my green one. I'll just go like this. There's it being scaled out there. So that green one is AB. That's this guy. So AB would be the one that we found down below. That's 5, 3. And that's going to be scaled by some scalar T. Okay, and that T, when I multiply that scalar in, is going to end up giving us that whole vector AP. All right, so let's do a little simple multiplication here, a little simple actually vector operations. Just going to bring this xy down, and we're going to distribute that scalar into that second vector, so we're going to have 5t plus 3t. And now we're going to add those two vectors together. So we have the vector xy is equal to the vector. Now we're going to add components here. Negative 2 plus 5t, or 5t minus 2, and then 3t plus 3. Just adding those two vectors together to get our resultant vector. So basically what we're saying here is the blue vector plus this vector here, that is the green one scaled out, is going to equal the resultant vector, that red vector right there. So look at the statement that we have here. xy equals 5t minus 2 comma 3t plus 3. Now we can set our components equal. We know that x is going to equal 5t minus 2, and y is going to equal 3t plus 3. And those are two parametric equations that represent that line. Okay, without any restrictions on t, that would represent the line that goes through those points forever and ever, for all values of t. Now what the next example says is find a parameterization of the line segment. So now we want a line segment where A and B now are endpoints. So we don't want that whole line anymore. We just want the line segment from A to B. We want to find out what that would be. Well, the nice thing is it'd be the same two, so we start writing our answer down here. It'd be the same two parametric equations, 5t minus 2, and y would equal 3t plus 3. But now we need to figure out what are the restrictions on t that we would need. Well, the way that we're going to do that is we're going to use the x values from those endpoints, and we're going to use the equation for x, which is x equals 5t minus 2, to find out what t should be. So I'm just going to use that x equals 5t minus 2, and I'm going to put in, I know that the first x value that I have here for my first endpoint is negative 2, so I'm going to put that in for x. I'm going to find out what t should be. So I'm going to add 2 over and get the 5t equals 0. Well, that just means that t equals 0. So when t equals 0, we should get negative 2. Well, if you look at our two equations here, if I put in 0 for t, then I definitely do get x equals negative 2. But an even better thing to check here is the fact that when we let t equal 0, we should also get a y value of 3. Let's see if that happens. If we put t equals 0 in there, we would get 3 times 0 plus 3. That would have y equal 3, which is good. It should be. Okay, so that just kind of worked itself out. So we know that t equals 0 is going to be one of our endpoints of our interval for t. The next thing that we're going to do is use our other x value, which is 3. I'm going to do it right here to find out what t should be. So we have 3 equals 5t minus 2. I'm going to add 2 over, divide by 5, and I get t equals 1. So if t equals 1, I know that x would equal 3, and y should equal 6, which it does if you check that back into the y equation. That would give me the point 36. So these are our endpoints for t, so we need to just add that to our two parametric equations. And in order for this line to become a line segment between those 2 points, t would have to be restricted between 0 and 1. That would now make that a line segment instead of just a line. Okay, sticking with that same idea here in this bottom problem, you can go through. Oops, I must erase something here. You can go through. Get rid of this right now. The eliminating the parameter here. Pause the video and try eliminating the parameter on your own. This is the same thing we did on the front side. I just did a little substitution, and I came up with this equation here for y. This would be the equation of the line represented by these two parametric equations. But here's the difference in this problem. That now this says with the parametric equations, we want t to be between 3 and 5. So what I did here, and I'm not saying you need to use a table, but I think a table works kind of nice for this, is I put in 3 and 5 into my two parametric equations. When I put in 3 and 5 into both equations, I came up with these two x values, and I came up with these two y values. That tells you the endpoints of this function, or actually it tells you the endpoints of the domain and the endpoints of the range. So along with this equation, what we're going to say is, along with that function, this is not a line, this is a line segment. So I'm going to actually include that. This is the line segment whose endpoints are 3, negative 3, and 7, negative 11. And we can give that as a domain and a range as well. Our domain is going to be x is everything from 3 to 7. I'm just using my two values here. Y is everything from, you got to be careful here, make sure you put your smaller value first. So y is going to be everything from negative 11 to negative 3. Negative 11 is smaller. So this is a line segment along this line, but with the accompanying domain and range.